Hello, in this video we will be reviewing the numerical series worksheet. So the first problem gives us the series of -1 to the n over n. And right off the bat we can tell that this will be an alternating series test because of the -1 to the n. So if you see the -1 to the n, then you will know you use AST, or alternating series test. And because the instructions asks us to specify absolute or conditional convergence when necessary, we'll know to test for this because it is alternating. So to do that, to check if it's an absolute convergence, an easy way to test that is to just see if the non-alternating version of the series is convergent or not. So the non-alternating part will be 1 over n, and that is divergent because it is a harmonic series. So therefore it cannot be absolutely convergent. So now we can just test to see if the actual series is convergent or not. And we can find that using alternating series test. So we can see that it is decreasing because the denominator increases faster than the numerator. And then we can also check to see the limit as n goes to infinity, which is equal to 0. And therefore, it satisfies all the necessary requirements for the alternating series test, and therefore, the actual series itself is convergent. So because it's not absolute convergence, then it has to be conditionally convergent. And that's your answer. A common mistake here would be to forget to check for absolute convergence and conditional convergence. So you have to remember to test the non-alternating part. The second problem gives us the series of 1 over n squared plus n. The first most common test used is the direct comparison test. So we can compare it to 1 over n squared, which is greater than 1 over n squared plus n, because the plus n makes the denominator greater. And 1 over n squared converges by p-series because this value is greater than 1. So because this is convergent and this is smaller, then that means by the direct comparison test, the series must be convergent. A similar strategy used is to use the limit comparison test, where you make b sub n equal to 1 over n squared, and we know that's convergent by the p-series. So then, if you do the limit as n goes to infinity of a sub n divided by b sub n, you would get the limit as n goes to infinity equals 1. And because that's greater than 0, we know that the limit comparison test can be used, and because b sub n is convergent, then that means a sub n is also convergent, which means the series is convergent. For the second part of the problem, it asks to find the sum if possible, and for this series it is possible because it can use a telescoping series. So we will tackle it that way. With the idea of telescoping series, we can write out the limit of the whole series by splitting up the actual series with a PFD. So if we split up the actual series into 1 over n times n plus 1, and then we use a PFD, then we can start plugging in these values to see the pattern. So once you plug it in, you'll see that the 1 will not cancel, but every term after that, up until the final term, will cancel out. Therefore, it will just be the limit as n goes to infinity of 1 minus 1 over n plus 1, and that's just equal to 1. So therefore, the sum of the series is 1, and the telescoping series is actually another strategy to prove that this is convergent, because you can find the sum of it. Number 3 gives the series of cosine 2n over 1 plus 3 to the n. The strategy for this is to see that you can use the direct comparison test very easily, and this is definitely the easiest test to use. So we know that cosine 2n is bounded between -1 and 1. So therefore, it is smaller than 1 over 3 to the n. So with that, we can easily use a direct comparison test. So if we set cosine 2n over 1 plus 3 to the n is less than 1 over 3 to the n, then we can see that this is a geometric series of 1 over 3 to the n. And 1 over 3 to the n is convergent because 1 over 3, the absolute value of 1 over 3 is less than 1. So therefore, because this is convergent and this is smaller, then that means this series is also convergent. And for this problem, you cannot use conditional or absolute convergence because it is not alternating, and also you cannot find the sum because it is not directly a geometric series or it's not a telescoping series. Number 4 gives the series of 1 over n times ln of n. A good strategy to apply here is the integral test, because the integral of this function is very simple. Whenever you see a function that is easily integratable, then you should do it. So if we take the integral of this and u sub, we would get 1 over n is equal to du, and then we can substitute that back in with n times du. So then n times du would cancel out with the 1 over n. So that would be 1, and then you substituted u for ln of n. So then you would get 1 over u du. And then this would be the integral from 1 to infinity, because our original series was from 1 to infinity. So that would be equal to the limit as t goes to infinity of the integral from 1 to t of 1 over u du. And that's equal to ln of u with these bounds, and then that would be the limit from t goes to infinity is equal to ln of t minus ln of 1. And that's using the fundamental theorem of calculus. Since this is equal to infinity, ln of infinity is equal to infinity, that means that this is divergent because the integral is equal to infinity. So a common mistake in this problem is that you would see this problem and first think that you could use the p-series because this bottom part is greater than 1 over n. But that is wrong because you need to check to make sure that it actually works, because this itself is not a p-series. Number 5 uses a very similar strategy to number 1 because it is an alternating series. Therefore, the alternating series test can be applied. So, because it is alternating, we can check if it is either conditionally convergent or absolute convergence. So, to check for absolute convergence, we can straight up just check if the non-alternating version is convergent or not. So to do that, we can use the ratio test. So we substitute n plus 1 for all the n's in the original series, and then we divide by the original series. And so that limit as n goes to infinity would be equal to half if you simplify. Because over here, 2 to the n would cancel with this 2 to the n, and you're left with 2 to the first. Then this top part would cancel with the bottom part to just leave you with 1. So then you would get half is less than 1, and because it is less than 1, that means the ratio test applies, and therefore it is convergent by the ratio test. Because the non-alternating version is convergent, then that means the actual alternating series is convergent too. So therefore it is absolutely Question number convergent. 6 gives the series of 3n squared plus 5 over the third root of n to the 7th plus n to the 4th plus 2. So the limit comparison test is very easy to use in this problem, because you can see that you can compare this with a p-series because the first two terms can be canceled out later on. So if we use the limit comparison test, we can set b sub n to the first two terms here, and that would simplify to 1 over n to the 1/3. And because 1/3 is less than 1 by p-series, b sub n is divergent. So using the limit comparison test, if we do the limit as n goes to infinity of the original series divided by b sub n, it would be equal to the limit as n goes to infinity is equal to 3. Because over here, n squared over n squared would cancel, and then the third root of n to the 7th would cancel with the bottom 2. So then you're just left with 3 over 1 times 1 over 1. So because 3 is greater than 1, by the limit comparison test, this would be divergent because b sub n, which we compared it to, is also divergent. A common mistake on here would be to forget to use the limit comparison test, and then you might end up with simplifying wrong algebra, and then you do your limit wrong too, and then therefore you might get Since questions 7 and 8 are very similar to questions 1 to 6, we will be skipping them because the strategies used are very similar. For question 9, we are trying to find the error within 0.005 and the sum within the same error. So since number 9 is not an alternating series, we can use the integral remainder sum. That is a very important strategy for finding the remainder. So we can take the integral of 1 over x to the fourth and get the absolute value, which is 1 over 3n cubed. So then, if we set the integral to less than the error we're trying to find, then n will be the number of terms we need. So we get n is equal to 8.7358, and we need to round up because that will guarantee a smaller error. So we need 9 terms. Then, for part B, it asks to find the sum within the same error, so we can do the sum of 9 terms, which looks like this, and then you'll get around 1.0819. Number 10 is very similar to number 9, except that this is an alternating series. So therefore, the alternating series remainder sum will be used. So for part A, it's asking for how many terms are needed to be within that error. So based on the alternating series remainder sum, you can just list out the actual series and find when it is smaller than the error you're trying to find. And this happens at the 7th term. Then you have to round down because of the alternating series. So therefore, 6 terms are needed. For part B, since you need 6 terms to be within that error, you just take the sum of 6 terms, which looks like this. And if you plug that into your calculator, you will get approximately this answer. So that is the answer within the error of 0.0005. A common error that may happen is that you forget to round down, and because this one's smaller, you accidentally say that you need 7 terms. So that is the most common that's the most common error in this problem.